Okay, in this video we're going to talk a little bit about functions, what functions are. So functions map each element in one set to exactly one element in another set. Okay, so looking at an example, let's say I have a group of 4 people and I want to give them one fruit. I want to assign each person a fruit. So I might assign this guy an apple, and I may assign her a strawberry, and I might assign her an orange, and maybe this guy gets nothing. I don't know. Maybe I don't like him, right? This assignment from a person to a fruit, we would call a function, because each person gets only one fruit. Now, this is not a function if one person gets 2 fruit. All right, so they're greedy. Let's say I give them 2 fruit. They're greedy about their fruit. I don't know. This is not a function because one person is getting more than 1 fruit. And this is kind of the rule for function in general, is each element from what we call the domain, or you can think of this as a set of people that I'm assigning to a fruit, gets sent to exactly or assigned exactly one thing in the range, the set of fruits, for example, right? So a function takes an element of the domain, say a person, and maps it to an element of the range, say a fruit. So I'm giving each person exactly 1 fruit. Now, another thing that might happen is I may give, let's say I decide I want to give this guy a fruit and I give him an orange, right? So maybe he gets an orange. And that's okay. That's allowed because every person gets exactly 1 fruit, but one person doesn't get 2 fruits, right? So 2 people may get the same fruit, but as long as they don't get 2 fruits, we're perfectly fine. Okay, and that's kind of an example of a function in a more abstract setting. We're talking about, for the purposes of algebra, we're talking about functions from the real numbers to the real numbers, or in other words, from the number line to the number line. So we may take some x in the domain, so we're talking about x on the number line, and by our function, we're assigning it another real number. We call it f of x, the assignment of x under f. So for example, if x is my person, f of x is my fruit, right? And so our function f assigns each x exactly 1 value in f of x. And so the way we kind of see that is, you think of a graph. So if this is my value x, then the height of my graph, the height of my function, is f of x. That's the value that x here gets assigned to on this number line. So we put the number lines perpendicular, and that's kind of that's the way we do graphs, okay? But not important for right now. So we want to talk a little bit about assignment, right? So let's say our function is the square root of 5 minus x. So every x gets assigned to the number square root of 5 minus x. Our question is, what does f assign 5 to? Well, we write that as f of 5. And f of 5, so this is what 5 goes to, right? So 5 gets mapped under f to f of 5. And the way we can do that is just by plugging in 5 for x, right? F of x gives us a nice rule. So it tells us no matter what you plug in for x, f will give you this output, right? It gives you this number. It assigns to this number. So if we plug in 5 here, I have square root of 5 minus 5, okay? Well, if I have the square root of 5 minus 5, that's just the square root of 0. 5 minus 5 is 0. So f of 5 is 0. So if this is our picture of f, right, this guy, then if this was 5, f assigns 5 to 0 on the number line. Okay? Now let's think about another number here. Let's say f of 2, right? What does f assign to? So f of 2 is going to equal the square root of 5 minus 2. So I just plug in 2 for x. So that is going to be the square root of 3. 5 minus 2 is 3. So f of 2 is the square root of 3. Okay, let's look at another example. What does f assign 3 to if f of x is x plus 1 over x minus 2? Okay, so what do? We just go ahead and plug in, right? So f of 3, what f assigns 3 to is 3 plus 1 over 3 minus 2. Okay, so 3 plus a third minus 2. Well, I can go ahead and just add this 3 and this negative 2 to give me 1 plus 1 over 3. Now I can give these a common denominator. This 1 is the same as 3 over 3 plus 1 over 3, and that's 4 thirds. So f of 3 is 4 thirds. So if this is our picture here, 3, right here, gets sent to 4 thirds under f, under this specific f. So, okay. We think about functions as being both rules and objects, right? So if I talk about f of x, I'm talking about a function, and we kind of talk about it as if it's an object, but really it's a rule. And this rule says if I take in x, I output x plus 1 over x minus 2, okay? Now let's look at this idea of domain. So remember, domain is this set. So if we were looking at people, remember our first example of a function was talking about giving each person a fruit, exactly one fruit. Our domain is the set of people. So it's the set of, it's the first set we consider, the set that's getting assigned, right? So not the set that we're assigning to, but the set that's getting assigned to something, okay? So it would, in our case, be the people here. Looking at some common functions, so you have polynomials. So examples of polynomials are, they're very familiar to you guys. It's going to be x plus, let's say maybe x plus 4, maybe 5x plus 4, something like that. Maybe 2x squared plus 3x minus 1, maybe something like x cubed minus 2x plus 1. Just functions that look like that, where it's just powers of x and coefficients. The domain of those is all real numbers. So we can, no matter what we take x to be, f of x, which is a polynomial in this case, will give us a valid output, right? And so you can think about this like it doesn't matter what I plug in x here, I'll get a number that makes sense out, right? For roots, so for even roots, like the square root of u, or the fourth root of u, and so on, only u greater than or equal to 0 is in our domain, okay? What I mean by that is, right, we're always told that when, because remember, okay, our function that we were looking at, our functions here, we're focusing on functions from the real numbers to the real numbers. So we're only focusing on values in the real numbers that give us outputs in the real numbers. And so why that's important to this is if I have the square root of x, well, if x is negative, I don't get a real number. I get a complex number. I get I times the square root of x. But if x is positive, I do get a real number. So we require that x is greater than or equal to 0, okay? And the reason I use u here is because when I have u, what I mean by that is I might have something that looks like the square root of 3x plus 2. Well, I require that whatever is inside the square root be greater than or equal to 0. So I need 3x plus 2 to be either 0 or positive. Can't be negative. We don't allow it to be negative, otherwise we don't get a real number. Okay, so that's why our domain is restricted. We say it's a domain restriction. The inside of the radical has to be greater than or equal to 0 if the number on the radical is even. If it's odd, so for example the cube root of u, or the fifth root of u, and so on, then our domain is all real numbers. All real numbers make sense. And I challenge you to think about why that is, rather than just being greater than or equal to 0. For rationals, so we think about something like 1 over u. So let's think about 1 over x, right? If x is 0, this is undefined, right? Because we're not allowed to have 1 over 0. We can't have that. This is undefined. So whatever's in the denominator, let's say it's maybe 3x plus 12, we require that it's not 0. So that's where this domain restriction comes from, is that we can't have it be 0, because otherwise we're dividing by 0, and we're not defined. But we don't have a definition for dividing by 0. That's a big no-no in math. So we set the denominator not equal to 0 to figure out when our domain is restricted. Okay? So let's do some examples. Let's find the domain of the square root of x squared plus 2x minus 8. Okay? Now, we want to remember when I have an even root, I need this guy in the square root to be greater than or equal to 0. Because if it's less than or equal to 0, I have a negative number in the square root, and that gives me a non-real solution, right? That's going to give me something with I, a complex number. So I need whatever is inside of the square root to be greater than or equal to 0. So let's go ahead and do that. 2x squared plus 2x minus 8 greater than or equal to 0. Well, how do we solve this? I have a video on nonlinear inequalities, specifically quadratics and polynomial inequalities, that allow us to kind of talk about this inequality. So using those steps, we can go ahead and solve this. Our first step is to find zeros of the right-hand side by factoring. So we'll go ahead and factor this. I need factors of -8 that add to +2. Well, how about 4 and -2? So I can go ahead and rewrite this as x plus 4 times x minus 2, that needs to be greater than or equal to 0. Okay, so my zeros of this, or my roots, are going to be x equals -4 and x equals +2. So my next step is to draw my number line here and plot my zeros. In this case, my zeros are going to be closed dots because I have greater than or equal to. And remember, if any of this feels foreign to you or is confusing, go back and check out my video on quadratic inequalities. It's called Nonlinear Inequalities 1 or something like that, and figure out how to solve these because they are important for finding domain restrictions. Okay, now that I have my two regions, I need to pick test values between my zeros here. So I'll pick 0 here, I'll pick 3 here, and I'll pick -5 here. So testing out that left-hand side with these zeros. So testing out -5, I have -5 plus 4 times -5 minus 2. This is going to be a negative times a negative. Remember, I don't care what they evaluate to, so this is going to be positive overall. So in this region, I'm positive. Testing out 0, this gives me 0 plus 4 times 0 minus 2. This is a positive times a negative. Negative overall, so I'm negative here. And then testing out 3, I have 3 plus 4 times 3 minus 2. Positive times a positive gives me a positive, so I'm positive here. Now, remember, we're looking for when this left-hand side is greater than or equal to 0, so when it's positive or 0, so that's with this region here, from -infinity all the way up to -4, including -4, right, because we're less than or equal to, greater than or equal to, and then everything from -2, including -2, onward to positive infinity. So the region that I'm looking at, the interval that I need, is everything from -infinity to -4, including -4, along with 2 out to infinity. And this, remember, is the domain of f of x. These are all of the values that make sense to plug into f of x. That's what the domain is. It's the value of things that make sense to plug into f of x. So looking at my original example of the people, well, it doesn't make sense for me to talk about what, like if I have an alligator, what fruit I'm going to assign the alligator, because I was only talking about assigning fruit to people. That's what I was talking about originally. It was about assigning fruit to people. So we wouldn't even consider an alligator, right? So in this example, we're talking about taking square roots, and we only can take square roots of positive numbers. So it doesn't make sense to talk about when we're negative. So we exclude this region here where things are negative. And so our domain is everywhere where f is positive, where this guy is positive, where this left-hand side is positive. Okay, great. So next we want to find the domain of x plus 3 over 3x squared minus 27. Okay, remember, if we have a rational function, so something like 1 over u, we need to make sure that the denominator is not 0. So we take what's in the denominator and we set it not equal to 0. Because if it's equal to 0, we're dividing by 0, and that's a big problem. So what we do is we take 3x squared, which is our denominator, minus 27, and set it not equal to 0. And so we just solve this like a normal equation. So I can go ahead and I have 3x squared minus 27. My goal is to factor. I need to factor this, right? Because if I see a quadratic, my options are factor or use the quadratic equation. If you don't know how to factor, go check out my video on factoring. I have a couple on them. Just make sure that you are comfortable with factoring. So from this I can factor out a 3, and I have x squared minus 9 cannot equal 0. If I divide both sides by 3, 0 doesn't care, so I'm left with x squared minus 9 cannot equal 0. Now I can add 9 to both sides, or I can notice that this is a perfect square, either one. So two separate solutions here, I'll do either one. So x squared minus 9 is a difference of perfect squares, you might notice that, so it's going to be x plus 9 times x plus 3 times x minus 3 cannot equal 0. And then we work with the cannot equals just as we would the equal sign. So x plus 3 can't equal 0, and x minus 3 can't equal 0. So x cannot equal 3, and x cannot equal negative 3. If you want to do this the other way, you might add 9 to both sides, so x squared cannot equal 9. So taking the square root of both sides, x cannot equal plus or minus the square root of 9. X cannot equal plus or minus 3. Okay, how do we write that in interval notation? Well, we take everything but plus or minus 3. So writing that as an interval, we have everything from negative infinity up to negative 3, not including negative 3, along with everything between negative 3 and 3, not including 3, along with everything that comes after 3, not including 3. So this right here is the domain of f of x. Okay? Great, so we found the domain of f of x for this guy. Pretty simple, just some factoring. Yeah, and then I think that wraps up everything I have to say. This is kind of an introduction to functions, what they are, what they do, and what domain even means. If you found this video helpful, please consider liking and subscribing. Thanks.